Electrostatics. Now, welcome back. This is a series from our A-level and IB Physics course. You can use this video for many different exams, including the MCAT exam, IMath, and any international exam that deals with electrostatics. Now, initially in electrostatics, you're met with the idea that electrons can move from, atoms to atoms, but protons cannot, because protons are obviously in the nucleus of the atom, and so only the negative charges can be transferred. Now, the electrons were found to have fundamentally a charge of E. E is equal to negative 1.6 times 10 to the power of negative 19 coulombs. The equation that I've established over here, Q, will give you the amount of electrical charge in a number of electrons. So Q stands for the charge, which is measured in coulombs, and N stands for the number of electrons. Now, it's important to remember and understand that when you're talking about Q and electrical charges, you have to understand where the actual amount of charge for an electron came from. The most famous experiment in electrostatics, one of the most actually, could be the Millikan oil drop experiment. The Millikan oil drop experiment was an experiment through which this famous scientist was able to find that the amount of the fundamental charge of an electron is roughly negative 1.6 times 10 to the power of negative 19 coulombs. So his experiment was very fascinating. He didn't make some, he did have some accuracy issues at the beginning, but then he fixed it, and we found the fundamental unit of charge to be what we have today. This was the basis of all the things that we use regarding electrostatics, because the charge of an electron is really important. Also, at the same time, usually problems will ask you for the mass of an electron as well, like regarding whenever the electron is accelerating. And you need to know the mass of one electron is 9.1 times 10 to the power of negative 31 kilograms. Now, the basic and most fundamental stuff that you need to know about charges is the fact that like charges repel, whereas unlike charges attract. So that means that if you have a positive charge coming near a negative charge, they will attract each other. And this is actually true in chemistry. In fact, that's how, some of the bonds are created between partially negative charges and partially positive, parts, and they basically get attracted and they create hydrogen bonding, for example. So this is the most important and fundamental fact that you should know about charges. Fast forward to a couple of things later, you learn something about something called Coulomb's law. Now, Coulomb's law is an interesting law that actually talks about the interaction of force between these, charges, whether the interaction is repulsive or whether it's attractive. So if we have a positive charge here that's at a specific distance to another negative charge, if the first charge has a value of like 1 microcoulombs and the second one has a value of negative 3 microcoulombs, and the distance between them is like 0.2 centimeters, we can calculate the force that is going to be applied from one charge onto the another by the equation Q1 times Q2 over R square. So this is a fairly simple equation. It's kind of similar to Newton's law of gravitation. In fact, it's sort of very similar to that, because that one is also F equals to G M1 times M2 over R squared. However, over here, Q obviously stands for the amount of electrical charge, which is measured in coulombs. K stands for a constant number, which is 9 times 10 to the power of 9 Newton meter square over Coulomb square. And R is the distance between the two charges. Distance between the charges. Now, it's important to remember that this distance is measured in meters. Usually, a lot of the problems you're going to be seeing in electrostatics will deal with the concept of Coulomb's law. However, the problem is the problems you will find are mostly going to be in a much more different format, like the one that I wrote over here as an example. So over there, if you want to find the force, you just have to multiply 9 times 10 to the power of 9 by the amount of the first charge, which is 1 times 10 to the power of negative 6, by the amount of the charge of the negative 3 microcoulomb one. Now, you can put that in absolute value and write that as 3 times 10 to the power of negative 6 divided by the distance between them, which is 0.2. And, you have to convert the centimeters to meters which is just 10 to the power of negative 2. So that gets multiplied by 10 to the power of negative 2 raised to the power of 2. And by the way, usually the unit of charge, coulombs, is a relatively big unit. So we usually write the charges either in microcoulombs, which is 10 to the power of negative 6, or nanocoulombs, which is 10 to the power of negative 9. Sometimes even millicoulombs, but that's not, as common as micro and nano. Anyways, if you were to calculate this, the result would be the force, and the force is actually equal to divided by 0.2. That would be roughly around 6,750 newtons, and that's a relatively big amount of force because the charges are quite close to each other. The farther away you go from the two charges, the larger the amount of Coulomb's law force becomes. Now, if both the charges are actually negative, the force between them becomes positive, or attractive in other words. So if Q1 times Q2 becomes a number that's less than 0, that's when both of them are negative. That means the force between them is attractive. Sorry, the other way around. If one of them is positive and one of them is negative, the force between them is actually going to become attractive, because positive times negative gives you a negative number, which is less than 0. However, if the resultant of their multiplication is positive or greater than 0, then the force between them is actually going to be repulsive. And that's basically when the two charges are the same. For example, a positive charge times a positive charge is greater than 0. A negative charge times a negative charge would always give you an answer that's greater than 0, which means that the force between them is repulsive. Also, it's important to note some of the small details about the formula of this, and that is the fact that the force is inversely proportional to the square root of the distance, to the square of the distance. So F is inversely proportional to R squared. Force is inversely proportional to distance. All right, let's go ahead and take a look at a question which involves vectors in this chapter. So let's say we have three charges, a positive Q1 charge here that's located at a distance of 0.4 meters from a negative charge here, Q2. And this one is at a distance of 0.2 meters from another point charge that's at a distance of Q3. And if I ask you to find the net force, or F net, on the third charge, here's what you have to do. Let's say Q1 is 10 microcoulombs, Q2 is -3 microcoulombs, and Q3 is -2 microcoulombs. How can I find the net force acting on Q3? The first thing I got to do is I got to draw a free body diagram for the sum of the forces, or the forces acting on Q3. So I'm going to draw a dot here. I'm going to say this is Q3. Q2 is going to repel Q3 away. So I'm going to have an arrow going to the right, and that's the force of 2 on 3. Q1, however, is going to attract Q3. And so I'm going to draw an arrow that's going to the left. That's the force of 1 on 3. Okay, so it seems like I have to find the value of the forces and simply subtract them, because the vectors, or the forces, are acting in opposite directions. So let's go ahead and find the forces. F13 is going to be Q1 times Q2 times times Q3, divided by the distance between Q1 and Q3, which is, well, if you add up the force, the distances, 0.4 meters and 0.2, that gives you 0.6 to the power of 2. So if you were to go ahead and calculate that, that's just going to be 10 times 10 to the power of -6 multiplied by Q3, which is 2 times 10 to the power of -6 multiplied by K, which is 9 times 10 to the power of 9. Also, don't forget to put the charges in absolute values, divided by 0.6 squared, which is 0.36. So if you were to put that in the calculator, you're going to get about 0.5 newtons. Now let's find F2 on 3. That's the force of the second charge on the third charge. So that's just going to be K. Q2 times Q3 divided by the distance between them, which is 0.2 square. All right, so that will give us 9 times 10 to the power of 9 multiplied by Q2, which is 3 times 10 to the power of negative 6 multiplied by Q3, which is 2 times 10 to the power of negative 6 divided by 0.2 square. All right, let's find that out. 9 times 10 to the power of 9 multiplied by 3 times 10 to the power of negative 6 multiplied by 2 times 10 to the power of negative 6 divided by 0.2 square. So that will give us 1.35 newtons. All right, so now that we found the two forces, in order to find the resultant force, we have to say F net with an arrow on top to indicate that the force is a vector quantity, or sigma F is simply going to be the force that is bigger, which is 1.35 newtons, minus the smallest force, which is the 0.5. So that will give us a force of 0.85 newtons directed to the right. So that's the direction of the force. So this is how you can utilize the Coulomb's law in a problem that involves straightforward vectors. In fact, this is actually a relatively easy question compared to things you can get where there are triangles involved or things of that nature. So, in fact, if I were to give you a question that involved triangles, it would look something like this. This is something that's quite common in many electrostatic books or the A-level exam or the IB exam when it comes to vectors in electrostatics. So let's say we have 3 charges and they're at the vertices of a right angle triangle. Q2 is a negative charge, and over here we have another negative charge here. This is Q3. Let's say this is Q1. Let's say Q1 is actually positive and Q2 is also negative. So it's actually located, these 3 charges, at the vertices of a right angle triangle. And the vertices of the triangle are as follows. This side is 0.4 meters and this side is 0.2 meters. By following the rules of the Pythagorean theorem, we can also find the distance between Q1 and Q3. And we can say that it's going to be so that's going to be the square root of 0.4 square plus 0.2 square. 0.4 square plus 0.2 square, take a square root. So the longest side of the triangle is 0.44 meters. Now here's the deal. What do you do if I ask you to find the net force acting on Q3? So how can you find the net force acting on Q3? And let's say that Q1 is 5 microcoulombs, Q2 is negative 3 microcoulombs, and Q3 is actually negative 2 microcoulombs. Also, the distance or the hypotenuse is actually 0.44 meters. That's what I found in the beginning. All right, so the first thing you got to do is you got to go ahead and actually find the value of the forces acting on Q3. So you actually have to go ahead and draw a free body diagram for the charge Q3. So step number 1 is to draw a free body diagram. Also, feel free to pause the video and try to do this problem on your own if you have a little bit of knowledge regarding vectors. So this is Q3. Now, Q3 is going to experience a repulsive force from Q2. So I can draw an upwards arrow, and that's going to be the force of 2 on 3. However, Q1 is going to attract Q3. So this charge, Q3, is going to be attracted by Q1. So we're going to have a force that goes along the diagonal of the triangle, the vertex of the triangle, that goes downwards. We can call that force the force of 1 on 3. Okay. Now, as you can see, the force of 1 on 3 is not in the correct direction. It's actually getting applied at a weird direction, and you need to actually make up components for it so you can solve it. So you break up the F13 into components, and if you do that, it's going to look something like this. If we consider this white line to be the x-axis and the other one, the vertical, to be the y, we have one force acting in the y direction. That's the force of 2 on 3. And we have one force that is going in the third quadrant in a way, which is the force of 1 on 3. Now, the forces of F1 on 3 are as follows. So we have one component of that vector going in the negative y direction. If we break it down into its components, we have F13 in the y direction. And we have another component of that in the x direction, which is going in the negative x direction, and that's F13 x. All right, so this is the free body diagram, and we have the vectors now. We just have to calculate the forces and also find the components of this F13. Now notice that the angle created here is known as theta. So we can find that theta by actually calculating the angle inside of the triangle itself. Theta is going to be here, and the angle of the force is going to be an alternate angle to that. So both of them have the same angle. So you can find theta simply by using the tangent. So theta is going to be the tangent of theta, which is going to be the opposite side. That's 0.2 over the adjacent side, which is 0.4. So theta is simply the tan inverse of 0.2 over 0.4. So we can find theta by taking the tan inverse of that, 0.2 divided by 0.4. The answer is 26.5 degrees. Okay, so let's go ahead and try the second step, or step number 2. What we have to do now is find the components of the force in the x direction. So the component of the force in the x direction are actually going to be, well, it's going in the negative direction. So we can say that it's going to be F1 on 3. So that's the components of the force of 1 on 3 times the, okay, now in order to find out what trigonometric ratio you're going to use, you have to see whether that side is adjacent to theta. Because F13x is adjacent to theta, you can find it by using cosinus. So F13 times cosinus of the theta, which is cosinus of 26.5. And F13y is going to be F13 times sinus of 26.5. Now, you can go ahead and calculate F1 on 3, but the value of F1 on 3 is simply going to be 0.44 newtons if you put it in the formula. And the value of F2 and 3 can also be found using Coulomb's law again. So F2 and 3 is going to be K times Q2, Q3 over the distance of F2 and 3, which is the second charge and the third charge, and that's 0.2 meters. So 0.2 square. If you calculate this, the value should be 1.35 newtons. Okay, now that we know this, we can actually go ahead and find the sum of the forces, or the net forces. 0.44. So the value of F13y is going to be 0.44 times the sinus of 26.5. And that's going to be 0.19. Now, you can put a negative before 0.44 to indicate the fact that it's going in the negative direction. But you don't have to do that here because we know it's going down. We're going to subtract the forces anyway. F13x, on the other hand, is also going to be negative because it lies in the third quadrant, where both the x values and y values are negative. So this is 0.44 times cosinus of 26.5. And F13x is going to be 0.44 times cosinus of 26.5. That gives you a value of 0.39 newtons. Now, that one is going in the left direction, so you can write it as negative 0.39 newtons. All right, so here's going to be the deal. In order to find the resultant of the vectors, we're going to write x, and we're going to write y here. So we have the forces of the 1 on the third, so the force from the first charge on the third charge. In the x component, the forces are F13 cosinus of 26.5, which is, well, negative 0.39 newtons. And then the second force we have is the force of 2 on 3, which has no forces in the x direction, so it's just 0 newtons. And then the forces of 1 on 3 in the y direction are 0.19, and of course it's negative because it's going down. But F2 on 3 it's in the positive y direction, so it's 1.35 newtons. So the total amount of these forces is we have negative 0.39 newtons in the x direction and 1.16 newtons in the positive y direction. So the forces are going to act in such a way where you have the positive 1.15 newtons going up, 1.16 going up, and then the negative 0.39 newtons going to the left. So you can find the net force between them by taking or connecting both ends of the vectors. So the net force is going to be the square root of 1.16 square plus 0.39 square. So F net is going to be roughly around 1.2 newtons. And if the question asks you for the actual angle created between the forces, you're going to use tangent. And tangent of theta is going to be, theta is over here by the way, is going to be the opposite side, which is 1.16, divided by the adjacent, which is 0.39. So theta is going to be the tan inverse of 1.16 divided by 0.39. And that's equal to 71.4 degrees. So the force, or the net force acting on Q3, is 1.2 newtons at a direction of 71.4 degrees. So let's kind of recap on everything one more time. First, you draw a free body diagram. You break the forces that are in a diagonal way into x and y components. You calculate the amount of forces in the x and y component, and also you find theta by using the tangent of the triangle. And also following the rules of geometry, we know that if this is theta 1 and this is theta 2, theta 1 and theta 2 are going to be equal to each other because of the alternate interior angle rule. And after that, we can just go ahead and simply find the forces in the x and y direction, find the resultant, and find the angle or the direction of the force. Thank you for watching. Make sure you practice a lot. Stay tuned for more.